Last time we found this amazing, beautiful bridge between this function, which does not seem to be a polynomial. That's called a rational function, if you want to be technical. And this other thing that appears to be a polynomial. I'm using the word a bit loosely because it really is of infinite degree. It would be a polynomial of infinite degree. So that's okay. By using the word, I makes it easier to understand. Although I give up a little bit of the rigorousness. That's okay for now. And we made this bridge using the famous geometric series idea. What we want to do is elaborate on this just a tiny bit and see other very, very creative ideas that will help us find the bridge between this world of non-polynomials and the world of polynomials. All right, so on with that. Talk is cheap. Let's do it. Of course, there's always this underlying condition. You got to have it to where the absolute value of x is less than 1. That way that will be valid. If not, other bad things happen. In fact, let's explore that. This came from the idea that if I take 1 plus x squared plus x to the third all the way to x to the infinity, this would give me x to the infinity plus 1 minus 1 all over x minus 1. So if for example, absolute value of x is greater than 1, or let's just take the easier case. The other case is even more problematic. If x is greater than 1, that means it's a big positive number, say like 5 or 7, then this piece right here would grow infinitely big. So imagine if you have 7 raised to the infinity plus 1. That would be really, really, really big, and that would be equal to infinity. So now you'd have infinity minus 1 all over infinity minus 1. Then you have issues, but this infinity is much, much more powerful if this is x to the 7th. So after some work, you'd see that this would go crazy. It would go infinitely big. So bad things happen if x is bigger than 1. By bad thing, I mean things go to infinity. I guess that's not always bad. For example, if it was your bank account balance. What? Okay. Anyways, back to calculus. So, we talked about this last lecture. For me, it's yesterday. We have this convergence, and we want to exploit this to see if we can get other amazing connections between functions and polynomials. So the first thing you got to do is you got to shake loose the idea that this only works when you have x. There's really absolutely nothing special about x. It is so ambiguous. It's like a variable. We could replace anything else other than x. For example, r. R would work. So long as you have the same condition, the absolute value of r is less than 1, obviously it would still work. You could replace it with b. You could replace it with any kind of stuff. And so that's exactly what we're going to do. What would happen if you put here, instead of stuff, let's say we go with stuff is equal to negative x. Yeah? So then I have 1 over 1 minus negative x. That would be equal to 1 plus negative x quantity squared plus negative x the quantity to the third plus negative x quantity to the fourth, all the way to infinity. Okay? Now we could clean it up, and this would be 1 over 1 plus x, and that would be equal to 1 minus x plus x squared minus x to the third plus x to the fourth minus x to the 5 plus x to the 6, and on and on and on and on and on. And so lo and behold, by just making this simple little cute substitution, we get a brand new expansion of a brand new rational function, the one with a plus instead of the minus. And so we can add this to our list of functions that we know the convergence for, or the expansion for. By the way, the fancy name for this bridge is called the Taylor expansion. And so, for example, let's see if we can get this. Now we have another one. We have that the expansion for 1 plus 1 over x is completely connected to this alternating polynomial of infinite degree. Okay, we already had the other one. just a little while ago we had 1 over 1 minus x. That one is equal to 1 plus x squared plus x to the third plus dot 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 dot. So that's 2 of them already. Unbelievable. We're making such good progress. But wait, there's more. You can, as soon as you see that, you can think to yourself, well, if I could have replaced that stuff there with negative x, then what stops me from replacing it with other things? For example, x squared or x to the third, or any sort of x variation, or even other things other than x. You can get all sorts of crazy ideas here. You could generate a whole big family of connections between functions and polynomials simply by substituting some other stuff here. All right, let's do maybe a couple more of those, and then we'll see. So, for example, I could substitute some other thing. I could call x squared. Let's do x squared. So if we substitute x squared, but we're substituting into the one with a plus. So I'll remind you, the one with a plus was 1 over 1 plus x. That's equal to 1 minus x plus x squared minus x to the third plus x to the fourth, and on and on and on. So if I replace the x with x squared, the quantity x squared, then all I do is replace it with x squared here. And that gives us something like 1 over 1 plus x squared. And that's equal to 1 minus x squared plus x to the fourth minus x to the sixth, and on and on and on and on. And there you go, another expansion from what is apparently not a polynomial to what looks like a lot like a polynomial, although of infinite degree. Okay? The audacity of humans to think so infinitely. I love it. But wait, there's more. We can add this to our list of famous things. There you go. We've expanded 1 over 1 plus x squared. One more on our bridge of amazing expansion. It's amazing connection between things that don't look like polynomials and polynomials. So let's go on that same kind of thinking. What if we do something else, such as let me see here. Sorry. What if we take that one last expansion that we did, and so we have that we have that 1 over we have that, right? 1 over 1 plus x squared is equal to 1 minus x squared and x to the fourth minus x to the sixth. What if we do something a little crazy here? For example, what if we were to take the derivative on both sides? Or what if we were to take the integral on both sides? How about that? We slap an integral on this side with respect to x, and we slap an integral on this one with respect to x. We don't even know if this is allowed. And who cares? Like, sometimes you just have to have the guts to try something and see if it works. That's a big part of mathematics. First you try it, then you check to see if it's legal. I know that's not what usually you're told, but come on, you only live once. Let's try something that might be illegal, might or might not be illegal, and see what happens. If we take the integral on both sides, I know this is a famous antiderivative. I know it's arctangent, and so I get that the arctangent of x, that's equal to the integral of 1 with respect to x. Well, that integral with 1 with respect to x is just x minus the integral of x squared with respect to x. Well, that would be negative x to the third. And then we've got to do the antiderivative of x to the fourth. That is so easy. I could do it with my left hand. X to the seventh over 7 plus on and on and on. Boom. Look what we've got here. Boys and girls, this right here is amazing. On the left hand side, you got something very, very, very much not like a polynomial. And when I was a little kid, I never ever thought I would grow up and when I grew up think that arctangent was a polynomial. It just looks so much not like a polynomial. And look at it. It actually is a polynomial. X minus x to the third plus x to the 5. Again, I'm using the word loosely just because it sounds better. But because most people would think that polynomials have a finite degree. But we're allowing ourselves to have polynomials of infinite degree. If you're okay with that, then you have this beautiful equation where you say, hey, the arctangent is actually just a really, really big long polynomial. But wait, there's more. How many of you guys have heard of this famous constant pi? Pi is equal to the ratio between the radius and the half circle, right? If you take that ratio, the ratio between that and the radius, you get one r here, and maybe another r here, and maybe another r here. You get a total of a little bit more than 3 r's, but people have been trying to figure out the exact number for a few thousand years, ever since humans saw circles, and they probably saw circles right when they looked at another human. Oh, you have circular eyes or whatever. We've been looking at circles since the existence of humans. And forever people try to figure out this constant. You have all kinds of civilizations trying to figure it out. The Babylonians, Egyptians, Eastern cultures, Western cultures, everyone's trying to figure out pi. And so we did here in just a simple little modest community college calculus class, we can actually figure out pi by hand or how to compute it by hand at any given precision that we want. We're about to do that in about 20 seconds using this amazing bridge between things that don't look like polynomials and polynomials. Here's how it goes. Ready? On this equation right here, on that one right there, which is arctangent on the left and some crazy polynomial on the right, on that one right there, what would happen if I substitute x equals 1? Let's try that and see what happens. What happens if x is equal to 1? Then I would get that the arctangent of 1 is equal to 1 minus 1 to the third over 3 plus 1 to the 5 over 5 minus 1 to the 7th over 7 and so on and so forth. Okay, dot, 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 dot. Now, I know arctangent of 1. Let me make a little thinking bubble here. Thinking bubble. Tangent of what gives me the ratio of 1 over 1. Or you can just, first of all, it starts off with ratio of 1, which is the same thing as 1 over 1. So I'm thinking that the ratio is 1 to 1 of the opposite compared to the adjacent side. And so I'm thinking, what angle gives me this? Sorry. And clearly, that only happens on a 45-degree angle, where the opposite side is the same as the adjacent side. That's got to be a 45, 45. So this gives me, then the arctangent is pi over 4. Pi over 4 is equal to 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9, dot, 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 dot. And so then by multiplying both sides of this equation by 4, I'll multiply the left side by 4, multiply the right side by 4, that gives me this incredible statement that says something about pi, the constant that has fascinated civilizations since the beginning of humans. It gives me that pi is equal to 4. Here I'm multiplying the 4 times 1, the 4 times that, 4 times that. So it'll give me 4 minus 4 over 3 plus 4 over 5 minus 4 over 7, dot, 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 dot. This, my friends, is an amazing statement. I've written pi as a just combination of adding and subtracting fractions. That, my friends, is beautiful. Do you guys know why poetry was invented? Do you guys know why math was invented? To woo women. That, my friends, is nice. All right. So, anyways, this is a timeless little piece of discovery brought to you by the connection between the two worlds. The world of functions that don't look like polynomials and really, really long polynomials. Now we could do this a bit longer, but I'd rather let you try to experiment with some of these. The point is that lots of functions, we did lots of functions today and we connected them to their polynomial. We started off with the most innocent looking one, that was 1 over 1 minus x. We changed that to 1 plus x. We did that. We did arc, tangent, and really you could do a bunch of these using these. You could find the bridge here using these cute little tricks, cute and creative, beautiful tricks. I'll call them ideas. But the truth is that there are other functions like sine of x, e to the x. By the way, just for as fun, you should take the integral of this one, and you'll get an expansion of the ln function, real easily. That's for you to do as homework. But okay, so these we could do using these very, very creative, cute ideas that exploit the geometric series at the heart of it. Now there are other functions like sine of x, e to the x that I don't know how to exploit these cute little ideas to get. But there's a much, 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 much bigger idea that will translate any, well, not any, but any function that has an expansion. There's this cute little idea that will, well, it has a Taylor expansion, I should say. There's a more general idea that will help you, and this idea is super, super creative. One of the most creative ideas you'll experience in all of your college career, probably in all of your life. This creative idea that will take almost any function, let's say any nice function, and it'll expand it into its Taylor polynomial. That idea is super, super, super amazing. We've got to develop that, but right now it's not the time. I'm just telling you what things we can look forward to. We've got to do that, and we also got to talk a lot more about these polynomials. It turns out that if things go bad, for example, if you pick a large value of x, like x equals 7, this polynomial is nonsense. It'll just go to infinity or won't even converge. So there's a huge, huge discussion about determining which of these polynomials are valid and which ones are just nonsense. And so that, the technical name for that is some of these converge, some of them don't converge. If they don't converge, we're going to call them nonsense. Or the other way around. If they're nonsense, we're going to call them divergent. A lot more to talk about. That requires a lot of careful analysis of these series and studying which tests. There are different tests that we can use to see whether they converge or not. And when is this bridge valid and whatnot. There's a lot of other details, but I wanted to get the main idea out and some of the power, like we just saw, like, for example, calculating pi to any given accuracy, just to show off, just to whet your appetite for this amazing ideas. All right, I think I should stop here. We will come back with more. See you guys.